But I just want to go over a couple of examples on forming differential equations from rates of change, and then we're going to go on to looking at solving them. So this is actually a complete recap from what you were doing before Christmas. So copy these down if you want to, but there's no need to copy them down particularly. But just to remind you what we were doing. So example 1, we've got an object moving through a liquid so that the rate at which its velocity decreases is proportional to its velocity. And we can form a differential equation from that. So the rate at which its velocity decreases is dv dt. So that's the rate of change. And it's proportional to the velocity. Because it's decreasing, we put a minus in. So it's got a negative gradient. Remember, k is a positive constant and it's proportional to the velocity. If it was inversely proportional to the velocity, just trying to remind you, then it would be minus k over v instead. Bit of rub off, right? When it enters the liquid, it has a velocity of 5 meters per second and the velocity is decreasing at a rate of 1. So we can now use that information to find k. So if it's decreasing at a rate of 1, then the gradient, so if you imagine you plotted the graph of the velocity against time, it's decreasing, you're finding the gradient in that graph. So at the point it enters the liquid, the gradient would be minus 1, so that's your rate of decrease, so negative. And that's equal to minus k times the velocity, which is 5. Remember, you're expecting k to come out as a positive constant. If it doesn't, then go back and think about where you possibly should have put a minus. Minus 1 over minus 5 is a fifth, and so k is equal to 1/5. And so dv dt is equal to minus 1/5 v, or v over 5 if you prefer. So that's the first one. So that's just a quick recap on proportionality. You might have to link together different variables as well. So second example. It's here. I'm hoping this is coming out because I've got a low battery. Fingers crossed. A spherical metal ball is heated so that its radius is expanding at the rate of 0.04 millimeters per second. At what rate will its volume be increasing when the radius is 3? So we want the rate of change in the volume. The volume of a sphere, you don't have to know these, but the volume of a sphere is 4 over 3 pi r cubed. So these questions tend to involve a volume or an area, which you have to differentiate. And so that's kind of your first port of call. So I need to differentiate the volume with respect to r, because that's the only variable I have. Timesing by 3, we end up with 4 pi r squared. So timesing by the power, taking 1 off the power. And its radius is expanding at a rate of 0.04 millimeters per second. So we know that dr dt is equal to 0.04. And it's just a question of slotting all this together. So dv dt is equal to, so there's dv dr. Sometimes you have to flip these to get the v on top, or possibly here, but this one's a bit more straightforward. So it's dv dr times dr dt. And so dv dt is equal to dv dr, which is 4 pi r squared, times dr dt, which is 0.04. So that's 0.16 pi r squared. And we want the rate of change in the volume when the radius is equal to 3. dv dt is equal to 0.16 pi times 3 squared. Guilty confession, I don't have a calculator on me. So if you do 0.16 times 3 squared, and then you can leave that in exact form in terms of pi. I've popped a sheet in your folder, so if you work through that first, and then we'll go on to some new stuff.